universe unique? To answer these questions, we had to go back to the origins of our universe. But how do you go back in time? With the help of observations, calculations, and modeling. Dear traveler, welcome. Today we're off beyond our galaxy to explore one of the strangest structures in the known universe, the gravitational anomaly of the Great Attractor. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Today, our understanding of the universe is based on the cosmological model of the Big Bang and the expansion of the universe. This is the theory that is widely accepted by the scientific community, even if it is not the only one, and with good reason. It provides a convincing explanation of the origin of all known matter and of the configuration of the cosmos as we observe it today. It also explains many phenomena, such as the expansion of the universe. According to the prevailing Big Bang model, the universe came into being approximately 13.7 billion years ago. This precise moment marks the birth not only of space, but also of time, matter, and energy. At its origins, the universe was an extremely dense and hot entity, much hotter than it is today. As it cooled, various materials began to combine, gradually forming complex structures such as galaxies, stars, and planets. To better understand this, let's go back to the dawn of time. The standard cosmological model describes the Big Bang not as an explosion in space, but rather as an expansion of space itself. This means that from the very beginning, the universe expanded at an incredible speed and temperature. It approximately doubled in size every 10 to the minus 34 power seconds, continuously creating more space. At the moment of the Big Bang, the universe underwent an extraordinary expansion phase known as cosmic inflation. During this phase, it would have expanded by a factor of at least 10 to the 26th power in an incredibly short space of time, precisely between 10 to the minus 36th power and 10 to the minus 33rd power seconds after the Big Bang. During this period, space expanded at faster than the speed of light. To visualize this phenomenal growth, imagine the universe expanding from subatomic size to that of a golf ball in the blink of an eye. This process of rapid expansion was followed by the formation of the various fundamental forces of the universe in a fraction of a second. The omnipresent energy gradually metamorphosed into particles of matter and antimatter. When these two types of particle met, they largely annihilated each other, leaving behind neutrons and protons. Within minutes, these fused to form hydrogen and helium nuclei. It then took some 300,000 years for these nuclei to bond with electrons, forming complete atoms and paving the way for the universe as we know it. The discovery of the Big Bang theory was initiated in 1922 by the Russian physicist and mathematician Alexander Friedmann. While Einstein strongly supported the thesis of a static universe, this physicist discovered that general relativity allowed us to describe an evolving universe. This was the first time the concept of expansion surfaced. In 1927, the cosmological model of the Big Bang was set out, by Belgian astrophysicist and priest Georges Lemaitre in an article in the Annales de la Société Scientifique de Bruxelles. He also established the first estimate of the Hubble constant before the American astronomer who gave it its name. That's why in 2018, the International Astronomical Union decided to rename this constant the Hubble-Lemaitre law. In 1924, Hubble demonstrated the presence of other galaxies outside our own Milky Way. Thanks to the Hooker telescope in Los Angeles, the most powerful of its time, he was able to identify NGC 6822, a small galaxy in the Sagittarius constellation. Followed a little later by the Triangulum and Andromeda galaxies M33 and M31. In 1929, he postulated that these galaxies were moving away from each other at a speed proportional to their distance from the solar system. In other words, the further away a galaxy is from us, the faster it moves away. This is Hubble's constant, which confirms the theory of the expansion of the universe. To imagine the expansion of the universe, imagine a raisin bun baking in the oven. The cake representing the universe swells as it bakes, and the grapes representing the galaxies move away from each other without being modified. The Big Bang theory also predicts the emission of thermal radiation at the beginning of the universe's history. In 1964, the cosmic microwave background was discovered by two American astronomers, Arno Penzias and Robert Wilson. This fossil radiation would have been emitted around 380,000 years after the Big Bang, when the universe was smaller, denser, and hotter. The universe then expanded and cooled. The cosmic microwave background thus corresponds to the first instant when the universe became sufficiently sparse for light to propagate. In fact, it's because light was able to illuminate the universe and travel to our telescopes that we can trace it back to this instant. The question of the origin of the world has not yet been resolved. We still can't see back further than 380,000 years after the Big Bang. In fact, Sir Roger Penrose believes that there was no single Big Bang, but rather a cyclical succession of several Big Bangs. And perhaps our universe will experience further cycles of several Big Bangs, but more on that later. While we still haven't completely solved the mystery of the origin of the world, for the moment, the theory of the Big Bang and the expansion of the universe is the prevailing one. The space between galaxies is growing every day, and in theory, objects are moving away from each other at a speed of 2.2 million kilometers per hour at present, or 1.4 million miles. So does this mean that the galaxy next to ours is moving away at 2.2 million kilometers per hour, or 1.4 million miles per hour? No, because unfortunately it's not that simple. We are slowed down in the universe by huge clusters of matter, because matter is attracted to matter. Galaxies cluster together in clusters and superclusters. This is explained by the gravitational force. On a large scale, gravitation organizes matter to form stars, planets, galaxies, and clusters. It is gravitational force that dictates the motion of our planet around the Sun, and the Sun's motion around the Milky Way's supermassive black hole, Sagittarius A. But there's more. There's more. In the 1970s, scientists detected a massive gravitational irregularity, which is pulling us and all our neighboring galaxies towards it. This irregularity was named the Great Attractor. Here's what we see when we look in the direction of the Great Attractor. Not much to see, you agree. And yet, this region of the deep sky, almost 220 million light-years from us, is of paramount importance, and has been the subject of debate for almost 50 years, and for good reason. It seems to have a phenomenal, if not inconceivable, force of attraction. The Earth, the Sun, the solar system, our galaxy and its 300 billion stars, and tens of thousands of other galaxies around us are all attracted by the Great Attractor at a dizzying speed of 610 kilometers per second, or 380 miles per second. The Great Attractor is so strong that it can draw millions of cubic light-years to itself. It's the largest concentration of mass in our intergalactic neighborhood, and therefore the gravitational focal point of all the galaxies around us. Although this terrifying gravitational anomaly has been known since the 1970s, it's only in the last few years that we've been able to discover what really lies behind the mysterious Great Attractor. On this journey, we'll go back in time to the origins of the Great Attractor's mystery, to better understand the phenomenal gravitational force that is pulling us along at breakneck speed. We'll take the opportunity to explore the area around the Great Attractor and understand what surrounds us on a grand scale. We'll also answer the question you're probably asking yourself. Will we one day collide with the Great Attractor, or worse, get sucked into this gigantic mass? This journey will take you to the heart of our universe, carried along by cosmic currents, to understand the mystery of the Great Attractor, but also all that the quest to solve it has contributed to astrophysics today. Fasten your seatbelts and let's set off on a memorable journey to the heart of the universe's greatest secrets. Since ancient times, astronomers have sought to understand the position and movement of the Earth in the vastness of the universe. In ancient times, the prevailing model was geocentrism. According to this model, the Earth was immobile at the center of the universe. The planets orbiting the Earth followed complex trajectories, with the direction of travel changing on portions of the curve known as epicycles. But some astronomers, like Eratosthenes, had already understood that the Earth revolved around the Sun. In the Middle Ages, despite strong repression from the Church, a new model took hold, placing the Sun at the center of the universe, heliocentrism. This time, the planets of the solar system followed circular trajectories rather than complicated ones. Copernicus was the first to disseminate this model, which was simpler than the geocentric model with its epicycles. Then Galileo discovered 4 moons of Jupiter, irrefutable proof that not all stars orbit the Earth. Galileo thus defended what was then known as the Copernican model against the Church, and took the opportunity to flesh it out. For example, he discovered that the trajectories of the planets around the Sun were not perfect circles, but ellipses, with non-constant speeds. Little by little, discovery after discovery, the heliocentric model gave way to the current one. We now know that the Sun is not at the center of the universe, far from it. It's just one of billions of stars in our Milky Way galaxy, and our galaxy itself is just one of 2,000 billion galaxies in the observable universe. And the entire universe extends far beyond our observable universe. We now know that the Earth's motion around the Sun does not describe a circle but an ellipse. The distance separating us from the Sun is therefore not constant, and varies between 147 million and 152 million kilometers, or between 90 and 95 miles. As for the speed at which the Earth moves, it's enough to make you dizzy. Imagine you're sitting motionless on the surface of the Earth. It's moving in its orbit around the Sun at a speed of around 30 kilometers per second, or 19 miles per second. If it's moving around the Sun, the latter is also moving, dragging the planets in orbit, including the Earth, at around 220 kilometers per second, or 137 miles per second, around the center of our galaxy. And since the middle of the 20th century, we can add to this the fact that our galaxy is plunging at more than 610 kilometers per second, or 380 miles per second, towards a mysterious region of the distant sky, the Great Attractor. But before we get to the mystery of the Great Attractor, let's take a moment to consider the discovery of the Earth's rotation. After all, the mystery of the Great Attractor has its origins in the movement of the universe and its components. We're going to talk about one of the most irrefutable proofs that the Earth rotates on itself. It's the famous Foucault pendulum. This pendulum was developed by French physicist Léon Foucault in the mid-19th century. It was first installed in the Paris Pantheon in 1851. Incidentally, the original version of this strange pendulum can now be found at the Musée des Arts at Métrez in Paris, but a Foucault pendulum can still be seen at the Paris Pantheon. What is the Foucault pendulum? At first glance, it looks like a simple pendulum, with a constant back and forth motion. You let go of the pendulum and it swings from point A to point B. It sounds so simple, but as I'm sure you've realized, in reality it's not quite that simple. Because once the pendulum has been thrown along a certain axis, it seems to deviate very slowly from that axis. Don't you think so? Look at the pendulum for a few minutes, and you'll see that the axis of oscillation gradually shifts. More precisely, because it has been measured, the Foucault pendulum deviates by more than 2 millimeters per oscillation. When small metal pins are placed on either side of the pendulum's initial plane of oscillation, the pendulum will gradually drop them, one after the other. Do you think it's the oscillation plane that moves clockwise and causes the pins to fall? In reality, the explanation is far more complex than that. A pendulum's plane of oscillation is fixed only by a point at its apex, and once launched, it will always maintain the same direction. Even if you were to rotate the support of the plane of oscillation, it would not deviate. But then, if the pendulum doesn't deviate, why do the pins fall one after the other in a clockwise direction? Quite simply, it is the Earth's rotation. It's not the pendulum that's off course, it's us that's spinning around it, or rather the Earth we're on. The movement of the Earth takes the Pantheon with it, and with it the table on which the pendulum stands. It's the skittles driven by the Earth's rotation that meet the pendulum, not the other way around. You're probably wondering whether the time it would take the pendulum to go round the dial corresponds to the time it takes the Earth to turn on itself, i.e. 23 hours and 56 minutes, or if we want to be really precise, 86,164.1 seconds. Once again, the answer is not quite so simple. At the North and South poles, it would take 24 hours for the dial to complete a full revolution. But in Paris, it takes just over 32 hours for the oscillation plane to return to its starting point. In fact, the closer you get to the equator, the longer it takes for the pendulum to complete a full revolution. In Cairo, for example, it will take 48 hours, and at the equator, the time it takes to go around the dial tends towards infinity. so on the face of it, you won't see it deviate. Let's take a moment to summarize. In the northern hemisphere, the apparent movement of the Foucault pendulum deviates to the right, and in the southern hemisphere, it deviates to the left. At the equator, it doesn't, or at least doesn't appear to. And that's not all. There's another curious thing about the Foucault pendulum. If we place ourselves at the North Pole and orientate the oscillation plane towards the Sun, we'll gradually see the Sun move away from the plane. In a few weeks, it will be completely out of the plane. If we repeat the same experiment with a star, we'll have to wait several years, or even millennia, before seeing the star move out of the plane of oscillation because it's located further away from us. As you can see, the further away the objects we're aiming at are, the longer it will take them to move out of the pendulum's plane of oscillation. Several conclusions have been drawn from these observations. 1. Motion is relative. In space, there is no such thing as absolute motion. An object is immobile in relation to another object. 2. Motion is dictated by the entire universe, not by our planet, the Sun, or the galaxy. Foucault's pendulum can only appear stationary on the scale of the entire universe. Many researchers believe that the world's Foucault pendulums point in the direction of the Great Attractor. In other words, the pendulum in the Pantheon, as well as those in Brussels, Barcelona, New York, and Los Angeles, all point in the same direction, that of the Great Attractor. Yet another mystery to be solved. To solve the mystery of the Great Attractor, let's start by tracing the history of its discovery. In the second half of the 20th century, space exploration made great strides thanks to new technologies, most notably the Hubble telescope. Thanks to increasingly powerful instruments, astronomers were able to observe more and more things, but they still had to be understood and organized. Little by little, a map of the universe began to take shape. The challenge was to find the precise position of our solar system and galaxy in the universe. In the 1970s, astronomers began to study the motion of the solar system and the Milky Way, and to compare it with the motion of other nearby galaxies. Everything seemed to be moving in the same direction, which could only be that of the expansion of the universe. But there was a curious twist that piqued the scientists' curiosity. In addition to the expansion of the universe, there seemed to be another direction, like a focal point towards which our galaxy and all its neighbors were heading. In fact, the Milky Way and its neighbors were not moving through space as they should have been. Instead, they deviated slightly from the direction induced by the expansion of the universe. It's as if we were adrift, carried along by a current. Many astronomers thought that this directionality was due to flaws in the observations. The scientific community wondered whether this observed effect was real or caused by a Malmquist bias. Malmquist bias is the bias we get in our observations of the cosmos because bright galaxies are easier to observe than dark ones. In other words, the Great Attractor wasn't immediately taken seriously. Scientists initially thought that the directionality observed was only apparent because of this bias. But as the 80s progressed, the mystery thickened and became difficult to ignore. Astronomers discovered that our galaxy and its close neighbors weren't the only ones drifting. All the matter around us for tens of millions of light years seemed to be drifting with us. The Milky Way, the local group, and the 60 or so galaxies it contains, the Virgo supercluster and its galaxies were all drifting in the same direction, towards an enigmatic region in the Centaur constellation. Technology continued to advance, and by the mid-1980s, astronomers were able to determine the speed at which we were heading towards this mysterious concentration of matter, 610 kilometers per second, or 380 miles per second. 610 kilometers per second, or 380 miles per second. That's enormous. Imagine that if our planet revolved around the sun at this speed, our years would only last 18 days. These discoveries have led to the identification of a mysterious, immensely massive structure that is said to draw all surrounding matter towards it. The mystery of the Great Attractor was born. Now came the hard part, finding the nature of the Great Attractor. Astronomers really tore their hair out to solve this seemingly unsolvable mystery. To be able to exert such an attraction on hundreds of millions of light years around it, the Great Attractor had to possess considerable mass. In fact, the mass required to attract so many cubic light years has been estimated at 50 million billion solar masses. A mass equivalent to 10,000 galaxies like our own Milky Way, concentrated in the same region. In the 1990s and early 2000s, the Parkes Radio Telescope in New South Wales, Australia, made it possible to study the sky with a new level of sensitivity. Thanks to this powerful telescope, astronomers were able to detect thousands of nearby galaxies and better understand the composition of the Milky Way. In the mid-2000s, the same telescope was used to study galaxies in the region of the Milky Way where the Great Attractor was thought to be located. And surprise, astronomers discovered that the Great Attractor was not located in the Milky Way but beyond it. Instead of solving the mystery of the Great Attractor, these discoveries only deepened it. We now knew that between the Great Attractor and us lay an enormous mass of stars and star clusters, as well as gas and dust. In other words, the Great Attractor is hidden from us by our own galaxy. Hidden by the edge of the Milky Way, concealed behind a veil of gas and dust, it appears difficult, if not impossible, to observe. Yes, because as we saw at the start of this journey, all we observe in space are objects whose light has reached us in the form of photons. That's why we can't go back any further in space-time than 380,000 years after the Big Bang. But the light coming from the Great Attractor, which would enable us to observe it and thus better understand it, is obscured by the veil of gas and dust in our own galaxy. This puts the Great Attractor in what is known as the avoidance zone. The avoidance zone is the region of the sky that is obscured by the plane of our galaxy, and which we cannot observe directly. This region, masked by the Milky Way's edge, is unfortunately quite vast, covering 1/5 of the observable universe. To observe it directly, we'd have to wait until the Sun, which revolves around the plane of our galaxy, is on the other side. But for that, we'd have to wait 100 million years. So does this mean that all hope of unlocking the mystery of the Great Attractor is lost? Not quite. At the turn of the millennium, the Great Attractor remained a complete mystery. Several hypotheses emerged to explain this monumental mass of matter that pulls us towards it at breakneck speed. According to the first hypothesis, the Great Attractor is an enormous collection of galactic superclusters containing millions of galaxies. The force of this supercluster would then be phenomenal enough to attract other superclusters, such as the Virgo supercluster. According to a second hypothesis, the Great Attractor would be an unusually high concentration of mass in a supermassive black hole of unprecedented proportions. And according to a third hypothesis, the Great Attractor could be the manifestation of an obscure force as yet unknown and beyond our imagination. An obscure force that could thwart the expansion of the universe. Fortunately, technological progress continued, and astronomers were soon able to see through the thick galactic clouds of our galaxy. For clouds of gas and dust are not completely opaque. They allow some radio, infrared, and X-ray emissions to pass through. Astronomers have been surveying these wavelengths with ever more powerful equipment, and have been able to make new discoveries. In the early 2000s, by refining the data and analyzing the readings, astronomers discovered a density of galaxies 220 million light-years away that was twice as high as normal. 600 galaxies have been observed in the region of the Great Attractor, but it has been estimated that it contains almost 4,000 galaxy clusters. Galaxies that have not been observed are those that are too small, too faint, or hidden by the galactic plane. Hoping to solve the mystery of the Great Attractor by exploring the hypothesis of a huge set of galaxy superclusters drawing us to it, astronomers turned their attention to the Shapley supercluster in the early 2000s. The discovery of the Shapley supercluster is well worth a closer look. Even if it wasn't enough to completely explain the mystery of the Great Attractor, it did solve half of it. The Shapley supercluster is located 650 light-years from Earth, behind the Ruler cluster. It was first observed in 1930 by the American astronomer Harlow Shapley, but it wasn't until the mystery of the Great Attractor began to take shape in the 1980s that astronomers became truly interested in this massive structure, which was then located north of the Centaur constellation. It is one of the most massive structures ever discovered in our universe. In fact, astronomers initially thought that the Great Attractor and the Shapley supercluster were one and the same. The mass of the Shapley supercluster is estimated at over 10,000 galaxies like the Milky Way. Compared to our local group, the Shapley supercluster is like an anvil next to a feather. The Shapley supercluster is located 650 million light-years away. At first, it was thought to be located in the constellation Centauri, but in fact it lies behind it. It contains at least 25 galaxy clusters, which are very close together as they are condensed into an area the size of the Virgo supercluster, which in turn contains only one large galaxy cluster. Astronomers at the University of Hawaii discovered in 2006 that everything around us flows as if carried by cosmic currents towards the Great Attractor, but that it is itself attracted by the Shapley supercluster. In 2015, astronomer Yehuda Hoffman of the Hebrew University of Jerusalem and his colleagues modeled the motions of over 8,000 galaxies and confirmed that there is indeed a flow of matter towards the Shapley supercluster, also known as the Shapley Attractor. Could the attraction that sends us hurtling at 610 kilometers per second, or 380 miles per second, towards the Great Attractor simply be the result of the combination of two attractions, that of the Great Attractor and that of the Shapley supercluster? To find out whether the Shapley supercluster could explain the mystery of the Great Attractor, this immense structure was studied by an international team of astronomers led by French astronomer Dominique Proust and Chilean astronomer Hernan Quintana with specialists from France, Chile, Australia, Brazil, and Argentina. The researchers carried out a dynamical analysis of the Shapley supercluster, using a number of cutting-edge instruments. The velocities of 8,632 galaxies were recorded, including 90% of the galaxies in the center of the supercluster and 61% of the galaxies in the supercluster. Several conclusions were drawn from these observations. Firstly, astronomers were able to identify ramifications between the Shapley supercluster and other superclusters, confirming the filament-like distribution of matter in the nearby universe. It was also discovered that the Shapley supercluster contains 44 galaxy clusters, and that those at its center are sources of X-ray radiation. This indicates the presence of very high temperature gas, over 10 million degrees. Each cluster has an oblong structure, due to the mutual gravitational pull of the galaxies within the cluster. The name God's Finger has been given to this strange structure. But all this doesn't give us many clues about the Great Attractor and the pull it exerts on us. Astronomers have also discovered that the galaxies in the Shapley supercluster have a much greater overdensity of matter than any known supercluster, and that the supercluster spans more than 120 million light-years, with a volume equivalent to an 80 million light-year sphere, making it the largest large-scale concentration of matter in the nearby universe. By near universe, we mean within a radius of less than 500 million light-years from us. So is this enough to explain the mystery of the Great Attractor? Not quite. Although very high, the mass of the Shapley supercluster is only half the mass needed to attract the local group to the supercluster. It wasn't until 2017 that the mystery of the Great Attractor was solved. Until then, the answer to our questions lay in the opposite direction to the one we were looking towards. A few years earlier, an immense empty space had been identified in the opposite direction of the Great Attractor. In 2017, Israeli astronomer Yehuda Hoffman confirmed the existence of this zone of emptiness and asserted that it acted as a repulsive dipole, pushing the local group and neighboring galaxy clusters towards the Great Attractor, located halfway in the direction of the Shapley supercluster. In fact, this repulsive dipole would act like the repulsive north pole of a bipolar magnet's magnetic field. Let's take a moment to consider this idea, which may seem counterintuitive to you. The vacuum repels. A vacuum is the absence of all matter, or at least with very little matter. Because the vacuum contains little or no matter, galaxies feel a lesser force of attraction as they approach the center of the vacuum. They then start moving in the opposite direction to the center of the void, as if repelled by the vacuum. Alternatively, the vacuum repels because it contains dark energy. In this case, it exerts a repulsive gravitational thrust on matter, accelerating the expansion of the universe. We'll come back to this dark energy hypothesis later. Here's a 3D representation of the Shapley Attractor at this dipole repeller, nearly 1.7 billion light-years wide. This 3D representation shows the repulsive dipole superimposed on the various galaxy clusters, with positive or negative gravitational potential depending on the region of the sky. This matter-free zone exerts a repulsive force that pushes all matter streams and galaxies towards the Shapley supercluster. In other words, everything between the repulsive dipole and the Shapley supercluster is dragged along by a kind of cosmic current, pushed into the arms of the Great Attractor at twice the speed predicted by theory. Let's summarize for a moment this discovery, which has sent shockwaves through the scientific community. We were looking for a cause for the attraction of the Milky Way and neighboring galaxies to the Shapley supercluster after discovering that its mass could only explain half of its attractive force. And we found a complementary force, this time repulsive, that can explain half the problem. The movement of the Milky Way, this plunge at 610 kilometers per second, or 380 miles per second towards the Great Attractor and beyond it, the Shapley supercluster, can therefore be explained by this repulsive, attractive movement, and not, as previously thought, by the pull of a single monumental mass, surpassing in size, mass, and power anything previously known. The astronomers were responsible for another major discovery, Laniakea. Laniakea is one of the largest known structures in the observable universe. Its discovery in 2014 caused a veritable earthquake. In fact, it was the discovery of Laniakea that led to a better understanding of the organization of superclusters and to the modeling of matter flows as cosmic currents. The Great Attractor is located at the center of this superstructure, this island continent. Continent is the right word. Laniakea stretches over 520 million light-years. Our galaxy, the Milky Way, extends over 100,000 light-years. In other words, we're a tiny speck on this immense galactic continent. What's more, Laniakea represents just 1% of the entire observable universe. But that's not all. The mass of this continent is estimated at 100 million billion solar masses. And Laniakea is said to contain 100,000 galaxies like our own, each with around 100 billion stars and 1 million dwarf galaxies. To imagine our position in the middle of this immense structure, it's as if the Earth were our home, the solar system our city, the Milky Way our region, the local group our country, and Laniakea our continent. The discovery of Laniakea represents a decisive step towards solving the mystery of the Great Attractor, just like the discovery of the Shapley supercluster years earlier and the discovery of the repulsive dipole a few years after that of Laniakea. As you'd expect, this discovery changed the way the scientific community and astronomy enthusiasts who had been following the Great Attractor's story closely viewed this strange unknown force. Dark matter is a theoretical entity invisible to our current observational instruments. It is said to be different from ordinary matter, that which makes up atoms, stars, planets, and by extension everything around us. Ordinary matter is subject to the 4 fundamental forces: gravitation, the weak interaction, the strong interaction, and the electromagnetic interaction. In contrast, dark matter is influenced only by gravity. To understand dark matter, it's crucial to understand that it remains to this day a theoretical concept. Although many scientists are convinced of its existence, other past theories, such as that of the ether, have already pointed to invisible material to explain certain phenomena. The concept of ether has long been an accepted and predominant element in scientific understanding of space and light. The notion of ether was conceived as an omnipresent, invisible, and impalpable medium permeating space, providing the necessary substrate for the propagation of light and other electromagnetic phenomena. According to this idea, just as waves require water to move, light would need the ether to transmit itself through the vacuum of space. However, this theory was later disproved by various scientific experiments, including the Michelson-Morley experiment, and more sophisticated theoretical analyses. These investigations led the scientific community to abandon the ether theory in favor of newer, more precise paradigms for describing the nature and behavior of light in the universe. The theory of dark matter was developed to explain certain gravitational irregularities in the universe, such as the movement of galaxies. Some believe that it could be a crucial component of the structure of the universe, present since the Big Bang. Why can't we observe it when we've managed to get through the veil of dust and gas of the avoidance zone to observe the Shapley supercluster 650 million light-years away? There must be some way of directly observing this dark matter if it's everywhere in the universe. But as usual, reality is more complex than theory. For dark matter is the opposite of so-called ordinary matter, which makes up everything around us: atoms, stars, planets. And unlike ordinary matter, it is not visible, as it neither reflects light nor emits it. It is thought to have appeared at the same time as ordinary matter during the Big Bang. Dark matter would explain why the universe is made up of galaxies and galaxy clusters, but also of voids, like the repulsive dipole. As mentioned above, ordinary matter is sensitive to the four fundamental interactions: the gravitational force, the weak interaction, the strong interaction, and the electromagnetic interaction. As a reminder, the weak interaction turns a proton into a neutron and vice versa. The strong interaction binds protons and neutrons together to form atoms, and the electromagnetic interaction holds atoms together. Dark matter, on the other hand, feels only the force of gravitation. It is not sensitive to the weak, strong, or electromagnetic interactions. If it exists, this strange hypothetical matter, this invisible double of ordinary matter, could force us to rethink all the physics inherited from Newton and Einstein. You must be burning with anticipation to find out more. So what exactly is the Great Attractor? A structure of dark matter? A phenomenal black hole incomparable in size to any other black hole ever discovered? A portion of an immensely gigantic supercluster? Or a mysterious, obscure force beyond comprehension whose existence we can't yet suspect? We're going to try to answer this question, even if, as you're beginning to understand, nothing is ever certain when it comes to the cosmos. Let's summarize the hypotheses that could explain the nature of the Great Attractor. The Great Attractor is a gigantic black hole. The Great Attractor is a mysterious dark force. The Great Attractor is at the center of a supercluster comprising millions of galaxies. Let's examine these hypotheses one by one. Let's take the first hypothesis. The Great Attractor is a gigantic black hole. The answer is no. Researchers are now convinced that the Great Attractor is not a black hole, but a gravitational anomaly. The Great Attractor is a totally different force from that of the supermassive black hole. In fact, it's more than likely that the Great Attractor has no connection whatsoever with a black hole. Yet the connection was tempting. The attractive force of a black hole is so strong that it attracts everything in its vicinity. We have theoretical proof that black holes can swallow stars. Nothing can escape the pull of a black hole, not even light. So we can't observe black holes directly because they absorb all light. So far, the resemblance to the Great Attractor is uncanny. But as far as we know, and according to scientific models that are more reliable than our earthbound imaginations, no black hole is capable of attracting so much mass of matter at such a great distance. Stellar black holes, the most common type of black hole, have a mass no more than 20 times that of the Sun. And supermassive black holes, the largest of the black holes, have a mass several tens of billions of times greater than that of the Sun, and that's still not enough. Let's take the second hypothesis. The Great Attractor is a mysterious dark force. Perhaps, but if it is, we don't yet know it, and we don't yet have the technological means to find out. So let's move on to the third hypothesis. The Great Attractor is at the center of a supercluster comprising millions of galaxies. This is indeed the case. The Great Attractor is at the gravitational center of the Laniakea supercluster. It is just one part of this immense supercluster, just as the Milky Way is just one galaxy among the 100,000 or so large galaxies that make up this supercluster. But what is the nature of this mysterious object at the center of Laniakea? Here again, there are various theories. Could it be an overdensity, i.e. a zone of dense mass with an intense gravitational attraction? Dark energy is neither dark matter nor ordinary matter. According to estimates, 74% of the universe is composed of dark energy. Dark energy has a negative pressure. It could explain the strange phenomenon of the accelerating expansion of the universe discovered in 1998. But why and how could it explain this phenomenon, which seems completely counterintuitive to us? It's quite simple. Energy is mass according to the theory of general relativity. So like all forms of mass, it gravitates. But gravitation is attractive. Logically, it should slow down the expansion of the universe, not speed it up. However, observations have shown that the expansion of the universe appears to be accelerating over time. Next to dark energy, which accounts for over 70% of the mass of our universe, the mass of ordinary matter, which is attractive, seems negligible. Understanding dark energy is crucial for astronomers. Depending on the variable nature of this energy, the universe could either end in a big crunch or continue to expand. The Big Crunch is not a very promising future for our universe. It's a cosmological model symmetrical to the Big Bang, in which the universe will eventually recontract after a phase of expansion. In this final phase of the universe, temperatures and density will rise again, and all material structures, such as galaxies, planets, atoms, and even nucleons, will be destroyed. The cosmos will then return to its post-Big Bang state of plasma quarks and gluons, and space-time will disappear with matter. Theoretically, the Big Crunch could be followed by another Big Bang, like a bouncing ball. There's one final hypothesis as to the nature of the Great Attractor that we haven't yet explored. In fact, according to some scientists, the Great Attractor may not exist. According to some researchers, the exact mapping of gravity fields would prove that the mass of known galaxies alone is enough to explain this phenomenon. And as disappointing as this solution to the mystery of the Great Attractor may be, it is perhaps the most likely. More on this later. In any case, whatever the nature of the Great Attractor, one thing is certain. Our galaxy and all that surrounds it are heading at full speed towards this region of the universe, this gravitational anomaly. Many wonder whether one day we'll collide with the Great Attractor, or whether we're destined to agglomerate in this region with all the other neighboring galaxy clusters in our local group. Above all, others fear that we'll be sucked into this gravitational anomaly like a star, swallowed by a black hole. Logically, this is what should happen. After all, if you look at the 3D modeling, all the flow lines converge at this point. It's as if the Great Attractor were a watershed, and the galaxies were rafts on fast-flowing streams. Astronomers are unanimous on one point. Whatever it is, the Great Attractor poses no threat to Earth, the Milky Way, or our galactic neighbors. Even if we are hurtling towards the Great Attractor and Shapley's supercluster, this drift is momentary in relation to the expansion of the universe. In time, however important this 610 km/s drift may be, the expansion of the universe, which continues to accelerate, will take over, and everything will be dislocated. Superclusters will be no more, and neither will clusters, so we'll never reach the Great Attractor or Shapley's supercluster. In other words, galaxies will continue to drift away from each other, faster and faster, while continuing to drift in the direction set by the Great Attractor. But before we've even reached our destination, the structure of the universe as we know it today will be destroyed. On the other hand, our galaxy will collide with something in the not-too-distant future, or rather with another galaxy, the Andromeda Galaxy, the largest galaxy in the local group. This collision will take place in around 4.6 billion years' time, and should result in a merger between our two galaxies, forming a new, even larger elliptical galaxy. The Milky Way and the Andromeda Galaxy are separated by 2.5 million light-years, but are closing in on each other at a speed of over 400,000 kilometers per hour, or 250,000 miles per hour. Despite the expansion of the universe, they will eventually collide. The end result will be the formation of a large elliptical galaxy called Milkomeda. In any case, this will have no bearing on the fate of life on Earth, for in around 4 billion years, the Earth will already have lost its ability to support life. This transformation will have taken place billions of years ago, following a drastic climate change, transmuting terrestrial conditions into a Venus-like environment due to the intensification of solar energy. Like the Andromeda Galaxy, the Great Attractor poses no threat to Earth. But understanding the effects of the Great Attractor's attraction remains important and is part of the quest to understand the structure of the universe. To study and understand the universe, it's important to know how it's organized, and above all, why it's organized the way it is. Knowing not only the interactions but also the characteristics of objects in the cosmos, from their dimensions to their mass, enables us to understand all these phenomena. What's more, understanding how the universe works also means understanding where we're headed. In other words, to study the future behavior of our universe. Especially as we won't be around to witness the end of this journey, if there is an end. What's certain is that the quest for a solution to the mystery of the Great Attractor will have enabled us to understand many things. It will have given us a better understanding of how the universe is structured and what forces are at work, even if we're still far from knowing everything. The Earth is neither immobile at the center of the solar system, nor embarked on a blind journey towards the Great Attractor, an obscure force that will eventually engulf us. It is nothing more than one of the many elements of the great cosmic web that is the universe, driven by a cosmic current that escapes us and that we don't perceive. Mapping the universe is like mapping a country, with its oceans, rivers, and watersheds, but also its currents and magnetic fields. The universe is a mosaic of cosmic flows that circulate around bubbles of empty space to form filaments of galaxies, which themselves flow in the direction of the current. And this flow is dictated by multiple forces, including but not limited to gravitation. Just as planets revolve around stars, on a larger scale, galaxies gather and flow around these centers of gravity. And all these movements, all these structures that form, are far from immutable. Everything will, in the very long term, end up being diluted in this great cosmic web. Thanks to all this knowledge of the structure of the universe gathered over time, astronomers have been able to produce dynamic maps of the universe with its void zones and galactic continents. Mapping the universe is a major challenge, because how do you represent a perpetually expanding universe where all objects are in motion and almost all matter is unknown? The geography of the universe is a geography of infinity, with ever-shifting and increasingly distant borders, a cartography that will always remain under perpetual construction. It's a geography that attempts to materialize the inconceivable and the immeasurable. Above all, it's a cartography of places we've never been, never directly observed, and probably never will see with our own eyes. What is mapped is what has been mathematically modeled from information gathered by ever more powerful instruments. So why tackle such a titanic task? Man began by mapping the sky, with the primary aim of finding his bearings in space. In 1650, the Paris Observatory was created so that French sailors could compete with the English Navy by having a reliable means of finding their bearings in space, the stars. But mapping the sky also enabled mankind to find its bearings in time. It was knowledge of the stars that enabled us to organize time into seasons, months, and years. Today, mapping the sky meets another need, one of the oldest of all time, the thirst for knowledge. We map the sky because we want to understand the universe and how it works. From mapping the sky, we moved on to mapping the solar system with the advent of the heliocentric cosmic model. But as our knowledge grew, our vision of the universe extended beyond the solar system, and then beyond the Milky Way. We had to increase the scope of our cartography. Today, with all we know about the universe, a fixed map is not enough. We need a dynamic 3D map. The cosmological model proposed by Einstein was that of a static universe. That was in 1915, before Hubble's discovery of the expansion of the universe in 1920. Or rather, confirmation, as we've seen that Lemaitre's earlier work also made a major contribution to the discovery of the universe's expansion. Excluding the relative motion of galaxies with respect to each other, Einstein had predicted a static universe, as the relative motion of galaxies were expected to cancel each other out. But today we know that this is not the case, and making static maps of the universe, like those of our countries on Earth, has no real value. On Monday, July 20th, 2020, an international team of astrophysicists presented the largest 3D map of the universe ever made, the Sloan Digital Sky Survey, or SDSS. This map required the collaboration of around 100 scientists from some 30 different institutions around the world over a period of more than 20 years. an optical telescope has even been specially dedicated to the project. It is located in New Mexico, USA. It all began in 2012 with the eBOSS project launched by University of Utah astronomer Kyle Dawson. The idea was to produce the most comprehensive 3D mapping of the universe. To achieve this, researchers analyzed over 4 million active galaxies and quasars. On this 3D map, you can see the famous filaments of matter we mentioned earlier, which structures the universe. Within these filaments, galaxies gravitationally attract each other and organize themselves into galactic continents, superclusters, which are themselves made up of clusters of thousands of galaxies. And in each of these thousands of galaxies, hundreds of billions of stars gravitate, and at least as many planets. This dynamic map is unprecedented in that it traces the history of the universe from its earliest moments to the present day. It's a continuous story that gives us a better understanding of the mechanisms behind its expansion. The publication of this map caused quite a stir, as we finally had a complete view of the history of the universe, where before we only had fragments. Another 3D map of the universe had just a year before the publication of the Sloan Digital Sky Survey caused quite a stir. We've already seen it, the map published by the international team behind the discovery of Laniakea. It took a real team effort to draw up this map. The glow of thousands of galaxies was measured using the world's largest telescopes, the Hawaiian Optical Telescopes, the Arecibo Radio Telescope in Puerto Rico, as well as orbiting telescopes which can see into the infrared. 3 years of work have produced an impressive dynamic 3D map of the universe in motion within a radius of 1 billion light-years around us. Helene Courtois and R. Brent Tully came up with the idea for this dynamic mapping method, which represented a real revolution, since until then, sky maps were detailed but static and ultimately unrealistic. In their view, this was the best way of exploiting the huge amounts of data collected over the years, a far more meaningful representation than a catalog listing data from thousands of galaxies. On this map, you can clearly see Laniakea, the large cluster in which the Great Attractor is located and which is heading towards the Shapley supercluster. On the map, we're just a tiny speck on the periphery of this egg-shaped supercluster of 100,000 galaxies, 500 million light-years across, and weighing 100 million billion suns. Mapping the dynamic universe is important, but it requires time, patience, and a gigantic database. To create this map of the universe in motion, Helene Courtois and R. Brent Tully measured for each of the thousands of galaxies, studied its 2-position coordinates in the sky and the speed at which it is moving away from or towards us. In other words, its redshift or blue shift. From this information, they deduced a measure of the galaxy's motion relative to the Earth. They then quantified the absolute luminosity of each galaxy and integrated this data into a cosmological model that masks the effects of the universe's global expansion. All this to deduce the galaxy's proper motion, i.e., the motion due to the action of gravity on matter. These calculations, brought to life on this 3D map, were used to model gravity currents, and thus to deduce the distribution of matter, whether observable or not. That's right, because the method used by these researchers makes it possible to guess the hidden matter. You remember, that which is masked by the plane of our galaxy. By tracing the currents on either side of the zone that appears invisible to us, we can make out its contours. In all, more than 8,000 measurements over a cube-shaped region, more than 1 billion light-years on a side, were needed to build this 3D model of our universe. And that's just 2% of the observable universe. Enough to make your head spin. Helene Courtois compares the cartography of our universe to the map of an alluvial basin. On both, there are converging slopes and watersheds. The team of researchers behind this dynamic map of the universe also examined the mystery of the Great Attractor. And they themselves are in favor of the theory that there is no Great Attractor. So we've been looking for a monster hidden behind the map of our galaxy for over 30 years, only to discover that it doesn't exist? Apparently it does. For this team of scientists, the explanation lies in a mass distribution different from that which had been calculated. In other words, they could see that all the matter was pouring into one particular spot, which appeared to be empty, and they were looking for what could be inside to attract so much matter. But in fact, it's like a watershed. All the water pours into the valley, but there's nothing to attract it there, only gravitational force. Now that the mystery of the Great Attractor has been solved, astronomical research will seem sad, or maybe not, for the challenges keep piling up. The next for Helene Courtois' team is to map the gigantic void that stretches out beside Laniakea. Largely masked by the light of the Milky Way, this void seems inaccessible to us, but the history of 3D mapping has taught us that nothing is impossible. What's more, this void, like the Great Attractor before it, is the subject of controversy. Its dimensions and repulsive force seem abnormal. In other words, it's too big and it pushes too hard. Could this vacuum be the result of an overdensity of dark energy? Could it be due to the presence of antimatter? One theory follows another with an air of déjà vu. It has taken almost 50 years to solve the mystery of the Great Attractor since the discovery of a strange deviation in the motion of the Milky Way and its neighbors. Today, most scientists are convinced that the Great Attractor doesn't really exist. In fact, what makes our galaxy and its neighbors plunge at 610 kilometers per second, or 380 miles per second, towards a precise point in the deep sky is the combination of the forces at work in the universe. The cosmic currents that have been highlighted by the latest discoveries in 3D mapping of the universe. The important thing to remember about this adventure is that it's not all as simple as you might think. Just because we're drawn in a certain direction doesn't mean there's a powerful magnet at the end of the road. On Earth, we are subject to several cosmic motions: the rotation of the Earth on itself, the rotation of the Earth around the Sun, and the rotation of the solar system around the center of the galaxy. On a larger scale, galaxies are subject to the expansion of the universe, which causes them to move away from each other, and to gravitation, the fundamental force of attraction. These forces create cosmic currents that form basins of attraction, within which the currents converge. Laniakea is one such basin, but the flow of matter is dominated by the Shapley Attractor, located beyond Laniakea in the neighboring Shapley supercluster. Cosmic current flows originate in the Great Repulsor or repulsive dipole and converge on the Shapley Attractor via the region long identified as that of the Great Attractor. And so, the mystery of the Great Attractor is finally solved. But in the cosmos, a mystery never stays solved for long. There are still many unexplained phenomena to which astrophysicists are still trying to find answers. Until the next great discovery,